Thanks a lot for the organizers for inviting me to give this talk. So yes, I'm going to be talking about expander codes and how to use them in order to achieve constant overhead fault tolerance. So the starting point is the well-known threshold theorem. So let me remind you of this threshold theorem while people are coming in. So the setting is that I have some circuit C, okay, that uses M qubits and T gates, so it's an ideal circuit, but I would like to implement it using noisy components. And so this fault-tolerant threshold theorem tells you that you can transform the circuit C into another circuit C prime that simulates C in the following sense, that if C has a given output R, then C prime also outputs R with high probability, even if the components, the individual components of C prime are noisy with a rate that is below some threshold P0. Okay, and so the important parameters, at least for this talk, that we want to discuss are the following, are the noise rate, the tolerable noise rate, as well as the space overhead. Okay, so ideally we would like to understand the trade-off between these two parameters, but we're very far from that. So my objective here is going to be a bit less than that, is namely to understand the space overhead needed, provided I just want the noise rate to stay constant. So I want P0 to be some arbitrary constant, and I want to know how small I can make the space overhead. Okay, so yeah, I want to emphasize that our point of view here is a theoretical point of view, so everything is going to be asymptotic, but just remark that, as was mentioned in this conference already, that this polylog term can be quite large in practice. Okay, so there are several works trying to improve this overhead, so in particular, for example, this work, so if you want to factor numbers which have 2,000 bits, then ideally you would need only about 4,000 logical qubits, but with noisy qubits you need more of the order of millions. Okay. Okay. Okay, so remember, so the main question I want to understand here is what is the minimum space overhead that is needed, this M prime over M, the number of qubits used by C prime divided by the number of qubits used by C. Okay, so and in this well-known fault-tolerant threshold theorem, this overhead is polylogarithmic in the number of qubits, M, and in the number of gates. Okay, so what I want to do in the next few slides is to understand where does this polylog come from. Okay, so that we can see how we can improve it. Okay, so in order to understand this, I think it's a bit simpler to understand the setting where we have perfect operations. Okay, so imagine it's only memory that is noisy, but I can do perfect operations. Okay, and we'll see very easily that this polylog comes from the fact of using concatenated codes. Okay, so suppose, yeah, so in this setting I want to store M logical qubits using some physical qubits which have a given noise rate, let's say P. Okay, so then probably the simplest method, so in the classical case would be just to repeat it. In the quantum case you can repeatedly use the 7-qubit code, for example. Okay, so let's see what this brings you. So if you store your M logical qubits without any encoding, okay, so you would have the number of physical qubits would be M, but the expected number of errors you would get would be P times M. Okay, so remember in this setting I'm seeing as M going to infinity and P as constant, so this is not very good. Ideally I would want the expected number of logical errors to be close to 0. Okay, so what I do is I encode each one of these qubits in 7-qubit code. Okay, so now I get 7M physical qubits. Okay, but now because this 7-qubit code can correct one error, okay, so then the effective error rate that I'm getting for each logical qubit is of the order of P squared. Okay, so then the expected number of logical errors is of the order of P squared times M. Okay, so again, this is still not good enough because P is constant and M grows. Okay, so I need to repeat this procedure several times. Okay, so how many times do I need to repeat it? So notice that if I repeat this k times, Okay, so notice what I mean by repeat is that I take each one of these 7m qubits and I encode it in a 7-qubit code. Okay, so I get 7 to the k m physical qubits, and now the bound on the logical error probability that I have is of the following form. It's p to the power 2 to the k times m. Okay, so if I want this number to be smaller than 10 to the minus 10, let's say, then I will need to pick k to be of order log m. Okay, and so as a result, the number of physical qubits I will need is of the order m times polylog of m. Okay, and so this is basically where the polylog comes from in the first slide I had. Okay, but at least in the setting with perfect operations where I'm looking just at storing information, then we know since Shannon that we can do much better than that. This is really not the optimal thing to do, but there are much better codes that can achieve m prime over m to be some constant. Okay, so and even more, Shannon in the classical case, he even characterized this, and this is just the capacity of the channel which has error probability p. Okay, so in the quantum setting, we don't know the capacity in general, but still we know that there exists good quantum error correcting code that can correct, that are constant rate and can correct a linear number of errors. Okay, so now let's ask the same question in the setting of fault tolerance. Okay, so now I don't just have m logical qubits, but I have a circuit that I would like to simulate. Okay, so then it's much more complicated, but you can do a similar construction in the sense that you start with a circuit C, you replace it by some fault-tolerant version of C, where you replace all the wires by you encode it in the 7-qubit code, and you replace the gates by logical versions of the gate. Okay, so again, when you do that, your error probability goes from p to p square. Okay, so you need to repeat this sufficiently many times to account for the errors in all the circuits. Okay, so if you do the same thing again, then what you would get is that you would need to take m prime. Okay, so the number of times you do the encoding to be log m, which means that the overhead, so m prime over m, will be polylogarithmic in the size of the circuit. Okay, yeah, by the way, C is not exactly the size of the circuit, but you can think of it as m times the number of gates. Okay, so now there is a very natural question, which is that we know for the setting with perfect operations that there are these codes which are much better than these simple codes that are obtained by concatenation. And the question is, can we use these for fault tolerance? Okay, so note that it's not at all obvious because there now your operations are noisy, and so you have to do all these operations, the logical gates, syndrome measurement, etc. And for general code, this seems very unclear how to do that. Okay, for a general constant rate code, it's unclear how to do that. Okay. Okay. Yeah, so I think this idea of trying to use constant rate code has been around for a long time, but it's only like a few years ago that Gottesman managed to use constant rate quantum error correcting codes that have some additional properties, not arbitrary quantum error correcting codes, ones having some additional, let's call them good properties that I'll mention later, in order to use them in the context of fault tolerance. Okay, so by using such codes, what Daniel could show is that is exactly what we want, is that you could construct your fault tolerance version of C, this C prime can use a number of qubits which is slightly more than m, so eta times m, where eta is an arbitrary constant that is bigger than 1. Okay, again, the result is very asymptotic, okay, so you have a little o of m here. Okay, and this simulates C in the sense that even if C prime has noisy gates and noisy memory with a parameter that is below some threshold which depends on eta, then you'll be able to simulate C. Okay, so I won't explain how this works. I won't go into how this works, but at the extremely high level, the ideal thing you would like to do is that take your circuit, which has m qubits here, to encode this in an error correcting code which has rate 1 over eta, okay, which has good properties. Okay, and then the challenge, of course, is to do all the operations like state preparation and applying gates within this code. Okay, so for example, if your circuit has some Hadamard gate somewhere in position I, then you would like to be able to replace that by the logical version of H bar, which should not propagate errors too much, and then error correct for the errors which would have propagated here. Okay, so actually, as far as I know, we don't know how to do this with just a single code, but what Gottesman did here is that he used not one block, but he decomposed these m qubits into polylog m blocks, each of size m over polylog m, and then encoded each one of them into a code of rate 1 over eta. Okay, so this ensures that you have some extra polylog m qubits that you can use while simulating a gate. Okay, so but I won't get into this. Okay, so what I'll focus more on in this talk is what are the good properties of a code that are needed and how to construct these codes. Okay, so the properties we need are very simple to state. So of course there's the constant rate codes. Okay, but we need additional properties in order to be able to do fault tolerance. Okay, so namely we need, or I won't say we need, at least it is sufficient to use low density parity check codes. Okay, so this means that the stabilizer generators act on a constant number of qubits. Okay, and so this is to ensure, in particular, that, for example, you can do the syndrome measurement in a way that doesn't spread the errors too much. Okay, so another property that is important is about error correction. So is that you need the decoder to be efficient, to prevent the errors from propagating too quickly, and it needs to be able to correct a random errors of linear size. Okay, and this needs to be the case even if the syndrome measurements are not perfect but are noisy. Okay, so these are the main properties I'm looking for. And in the rest of the talk, I'll try to tell you that these quantum expander codes, which I'll define, have all these good properties. Just a brief outline of how I'm going to explain this is I'm going to start first with these classical expander codes and how they are decoded, and then define the quantum version of these codes and how one needs to adapt a bit this decoder to change it instead of bit flip, small set flip. Okay, and then I'll give a brief sketch of how to analyze this small set flip. So first, we'll see for adversarial errors how we can analyze this small set flip decoder, and then how we can use the fact that we understand adversarial errors in order to correct random errors of linear size. Okay, so just to set up notation. So so the rate of a code is the number of encoded bits divided by the number of physical bits. Okay, so I'm going to use a parity check matrix. I'm going to say that the classical code is LDPC if in this parity check matrix the number of ones in each row and the number of one in each column is a constant, is at most a constant. Okay, so this representation in terms of graph will be useful. I put on the left the bits, okay, so the columns of my parity check matrix, and on the right the checks, which are the rows of my parity check matrix. Okay, so again, to set up the notation, so I'm going to consider syndrome decoding. Okay, so what I observe is the syndrome of a given error. So I have a given error that is applied on my code word. What I observe is a syndrome, and my objective, the computational problem, what I call a decoding algorithm, is an algorithm that does the following. It takes as input a syndrome, okay, sigma of E, and its objective is to find an E hat which has exactly the syndrome. Okay, so now let's get to expander codes. Okay, so these were introduced in 1996. So in the context of trying to find good codes which have linear time encoding and decoding. Okay, so yeah, so for these expander codes, I mean, they come directly from expander graphs. So it just means that I want my factor graph to be an expander graph. Okay, so what do I mean by an expander graph in this setting? So, let us consider graphs where the left degree is exactly d. Okay, so each one of these bits has exactly d neighbors. Okay, so or it's involved in exactly d checks. Okay, so notice that if I take an arbitrary set E, okay, of bits, then its neighborhood is of size at most d times E. Okay, this is direct. So what an expander graph is asking for is that this upper bound is almost an equality. So in the sense that I have a lower bound, that gamma of E is at least 1 minus delta times this value. Okay, so in other words, this means that the neighborhoods of different bits don't overlap too much. Okay, so how do I decode such a code? So basically, you take the simplest possible decoding algorithm, which is a very greedy algorithm. So remember, the objective of a decoding algorithm is you observe a syndrome. So you say that some of these checks are violated, are unsatisfied, and your objective is to obtain an E that gives you exactly the syndrome. Okay, so what you'll do is you'll look at each one of the bits, okay, of your code, and you try to flip it. Okay, if you try to flip it, you will be able to determine what is the syndrome after applying this bit flip. Okay, if the syndrome weight decreases, then you apply this bit flip. Okay, and you continue. Okay, so this is just the bit flip algorithm. You look for bits. If flipping this bit allows you to decrease the syndrome weight, then you flip it, and then in a greedy way, and then you continue in this way until your algorithm stops. Okay, and so the main theorem that was shown by Sipser and Spielmann here is that if you take a graph with an expansion which is sufficiently small, okay, so below 1/4, and if your error is sufficiently small, okay, so namely smaller than some gamma times n, okay, so yeah, think of gamma as some constant. Yeah, so if your error is below some constant times n, then the bit flip algorithm is able to correct this error E. Okay. Okay, so let me try to give a proof sketch of this, because maybe this will give an idea of how the expansion is used. Okay, so I want to show two things. Okay, so I want to show that yeah, so that at any time the algorithm is never stuck, okay, until it reaches an error which is 0, okay. Sorry, until it reaches a syndrome which is 0. Okay, so I have to show that at when I have E which is non-zero, so okay, so E is my actual error that happened. I don't have access to it, and yes, so I will show two claims in order to show this result. Is that first, that if the error happens to be smaller than some gamma n, okay, then there is a valid bit flip. Then the algorithm is not stuck. It can decrease the weight of the syndrome. Okay, so how do you show that? So here's where you use the expansion properties. So if you look at gamma of E, okay, so notice that E is smaller than gamma n, so you know that gamma of E has size at least 1 minus delta times D times E. Okay, so and because the maximum number of checks that are connected to E is D times E, then there must be many of these checks that have a unique neighbor in E. Okay, but notice that if you have a unique neighbor in the error, then this check has to be unsatisfied. Okay, so all of these are unsatisfied, and so because you have many unsatisfied checks, then there must be a bit, which call it E, such that if you flip it, okay, the syndrome weight decreases. Okay, so this is the high-level idea. Okay, let me not spend more time on this. And okay, so the other thing I need to show you is that so of course the error does not necessarily decrease as I'm applying this decoding algorithm. Okay, so as I'm applying the decoding algorithm, I might flip bits which were not in error at the beginning. Okay, but still we can show something which is approximately that, which is that at any time during the decoding, the total size of the error is at most gamma times n. Okay, so I start with gamma with a little bit less than gamma n, so it can go up to gamma n, but not much further. It can go up to gamma n, but that's it. It cannot go more than this. Okay, and this is basically by showing that by using the fact that by definition of this algorithm, the syndrome of my successive errors has to decrease strictly, right? This is by definition of my algorithm. At each step, my syndrome weight has to decrease. And because of the expansion, the weight of the syndrome and the size of the error are related by some factors d and factors of the form 1 minus delta. Okay, and so by using these two together, you can show that you will never go above gamma n. Okay, because you start basically with a syndrome which is not too large. Okay, and so you cannot go above an error of weight gamma n. Okay, maybe I should go a bit faster. Okay, so in the so now in the classical setting, we manage these expander codes. These are constant rate, are LDPC, and yeah, maybe I didn't talk about constant rate, but yeah, if yeah, I didn't talk explicitly about constant rate and LDPC, but so maybe let me say here that the way you would construct such an expander code is one way. The simplest way is to pick these checks, the number of checks to be a constant fraction of the number of bits here, and then to pick this graph at random. Okay, if you pick this graph at random with constant left degree and constant right degree, then you will have this property for a constant delta. Okay, and because the degrees are all constant, and the number of checks is a linear fraction of the number of bits, I mean less than 1, and so you would get the LDPC property and the constant rate property, and with this bit flip algorithm, you would be able to efficiently correct linear size errors. Okay, actually any linear size error, not even just the random ones. Okay, if it's below this gamma times n. Okay, so now that was for the classical setting. Now let me get into the quantum setting. So yeah, I only need CSS codes for this talk. So for me, yeah, so CSS code is given by two parity check matrices, Hx and Hz, which satisfy this property that the rows of the two are orthogonal. Okay, so here's just an example. Yeah, so by the way, I will use, so Hx corrects the x errors, and so they're z-type operators. Okay, so here I have the same thing. So I obtain the syndromes sigma x and sigma z, and my decoding algorithm is just about obtaining an error. Okay, so ex or ez, which explains the syndrome. Okay, and so again, this is what I'm going to be calling a decoding algorithm. Okay, so and because in this talk we'll actually have Hx and Hz be the same matrix, so we'll just focus on correcting x errors. Okay, so my objective is I want to get yeah, sorry, it goes the other way here. So I want to get Ex from sigma x. Okay, so yeah, so I'll be interchangeably using E as a bit string or a subset of 1 to n. Okay, and the syndrome corresponding to an error E will be denoted by sigma of E. Okay, so this was the notation. Okay, so now we want to construct hx and hz, which have these good properties, so namely constant rate and LDPC. Okay, but there's a difficulty here, which I'm sure many of you are familiar with, but maybe let's go over it quickly, is that, yeah, so if hx and hz are LDPC, then q is LDPC. Okay, this by definition. Yes, so it's sufficient if hx and hz both correct lots of classical errors, then the corresponding quantum code will correct lots of errors, will correct t quantum errors. Okay, but the problem is that it's not sufficient to just use the classical error correcting capabilities of hx and hz in order to understand what q does, especially in the LDPC setting. Okay, because namely there is a conflict between these properties, that I want hx to be LDPC, so I want its rows to be of constant weight, but I also want hz to correct errors of large size. Okay, but remember that I have this requirement that hz times hx transpose is equal to 0. Okay, so at least the rows of x are errors for hz, and they're of low weight. Okay, so yeah, these three things don't go together. So this is just to say that we need to use additional properties, not just the classical error correction capabilities of hx and hz, and I need to use the degeneracy here. That basically the thing I need to show is that I need to show that the rows of hx are the only low weight strings in the kernel of hz. Okay, so yeah, this was just to say that there is a difficulty here in constructing hx and hz in a way that the quantum code inherits these error correction capabilities. Okay, but but recently there was a very nice construction of codes which gives you exactly that, which you start from two good classical codes, and it gives you a construction of a quantum code with good properties. Okay, I should go faster. Okay, so here's how this hypergraph product code works. So I start with two classical codes. Okay, so the red code and the blue code. Note that they don't correspond to the hx and hz, they're different. Okay, and I construct a product code. Okay, so how is this product code defined? So let me start with the qubits of this product code. So I have two types of qubits. I have the VV type qubits and the CC type qubits, which are obtained as a pair of a bit of the first code and a bit of the second code. Okay, and CC is the same for the check bits. Okay, so I told you what are the physical qubits of my code now. Now I have to give you the generators. Okay, so for that I will use these two graphs, the blue graph and the red graph. So the red graph should be read horizontally here. So okay, so if I take a given column with indexed by some v2 here, okay, then I will just copy the edges which I had in the red graph. Okay, so for each column I will put this edge. Okay, and I do the same for the rows. Okay, so okay, so yeah, maybe I should have been. So I will get, so here in the top right corner, what I get is the Z-type generators. Okay, so now the graph HX. Okay, so remember, for me, quantum code is given by two classical codes. So the code CX, or parity check matrix HX, is given as follows. So the checks are given by this rectangle here. Okay, so each element in this rectangle is a check node. Okay, so it corresponds to a generator, so to a Z-type generator, and so its neighbors are given by I look at the edges corresponding to the blue graph in this way, and the edges corresponding to the red graph in this way. Okay, and so because, remember, we focus on X-type errors, then what I'm observing are the syndromes corresponding to these generators. 10 minutes, okay. Okay, so this is the X-type generators. Okay, so let's look at some examples of these construction. Yeah, so, okay, so we'll construct quantum expander codes using this construction. But first, let me just remark that if you take the two codes to be the simplest classical codes or repetition codes, then what you get out of this hypergraph product is the toric code. And the nice property is that if the two codes are LDPC, then the resulting code is also LDPC, and you can see that the degree corresponds to the sum of the degrees. Okay, and also if the two codes are equal, let's say, and have constant rate, then one can show that the quantum code also has constant rate. Okay, so this is it for the two first properties. Remember, we wanted LDPC constant rate. And now about the challenge is more in the decoding. But okay, yeah, first let me say what a quantum expander code is now. So a quantum expander code is just obtained by this hypergraph product code by taking the two codes to be classical expander codes. Okay, and the challenge here is to find an efficient decoder for this quantum code. Because in general, it's not clear that given a classical decoder for the corresponding classical code that this translates into a decoder for the quantum code. And actually, we'll see it right away here. Okay, so so now we have these our candidate codes. Now what we have to do is to define the decoders. Okay, and so this was done in this paper. So the first idea you might have is, because these are quantum expander codes, I might apply the simplest possible algorithm, which is this bit flip algorithm. But it turns out that this actually fails. Okay, so let's see it on this example. Okay, so remember the qubits are given by these two blocks, these two diagonal blocks. Okay, so imagine my error is this are these black dots. Okay, so these are my error, and they correspond to half of the neighbors of a given X-type generator. So remember, what I want to, the syndrome bits I observe are these ones, but I look at the neighbors of an X-type generator. Okay, and I suppose that half of the qubits are in error. And so it's simple to see that the corresponding syndrome will be this. Okay. Okay, but here you see, it's easy to see that if you try to flip any one of these black dots, let's say, then, so let's say if you try to flip this one, the top one, then this one will become not an error, but the one next to it will become an error. So the syndrome weight will still have size 4. Okay, so yeah, the bit flip algorithm is stuck here. But there is a simple fix to that, which is instead of, so remember what the bit flip algorithm is doing is it's considering a set of possible flips which are just the single bits, and you try each one and you try to see if the syndrome decreases or not. Okay, and but here for this example, it turns out that if you try any of the bits, no one decreases the weight of the syndrome. Okay, so now the generalization is to take this set of possible flips to be not just the bits, but to pick other well-chosen sets. Okay, so if F is well-chosen, it shouldn't be too large, otherwise it shouldn't be all the possibilities, otherwise the algorithm would take exponential time. So it should be a small set. This F should be ideally linear in the size of the number of qubits. And yeah. So you generalize it a bit, and so it turns out that the right generalization is to do this small set flip algorithm, where it's directly motivated by this example. So notice that in this example, if I try to flip a subset of the generators of an X-type generator, so for example, if I try to flip just the blue dots here, then of course my syndrome will go down from 4 to 0. Okay, and because the neighborhood of a given X-type generator is of constant size, I can try all the possible subsets. Okay, and so this is just the algorithm, and so Now what I will try is I will go over each one of these X-type generators, and I try to flip all the subsets, and if one of them decreases the syndrome weight, then I do this flip, and then I continue. Okay, so yeah, so it was shown in this paper I mentioned earlier that this algorithm, provided there is sufficient expansion, actually you need also expansion on the two sides, then the small set flip can correct an error of size root n, where n is the number of physical qubits. Okay, so actually root n turns out to be the minimum distance of this code. So you cannot do better than that. Okay, so, but remember what we would like to do for us is we would like to even allow for syndrome errors. Okay, so this is that even if my syndrome measurements are noisy, then I should be able to correct. So now the setting is as follows, is that I have a set of qubits which are in error, and I have a set of syndromes which are in error. Okay, and what I observe is not the correct syndrome, but the correct syndrome, so sigma of e qubit plus some errors. Okay, so what I can try to do, okay, so yeah, first in this case I cannot hope to fully correct the error. Okay, this is not hard to see. Okay, so but the hope is to control the error in a way that depends only on the size of the syndrome. Okay, and this is actually what we'll be able to show here. But so let me ask what is the decoder that we'll consider in this case? Actually, we'll consider the exact same decoder. Okay, so the same the small set flip decoder. I applied the exact same algorithm. So of course now the problem is that what the decoder sees is not the correct syndrome, but the noisy one. Okay. Okay, so I will try to just decrease the weight of the syndrome until I'm stuck. Okay, so with this notation, E final being the error on the qubits plus XOR was all the flips that were done by the small set flip. It turns out that you can control the final error in the following way. So if the error is sufficiently small, so if the number of errors on the qubits is of order of square root of n, then the final error, okay, we cannot guarantee it's 0, but we can upper bound it by the number of errors in the syndrome. Okay, so in the particular case where the size there is no errors on the syndrome, then this gives me back this theorem. But yeah, it's more general. Yeah, okay. Okay, so okay, so let me maybe go quickly over the proof here. So what I will try to do is that assuming that the final error is bigger than a constant times the size of the syndrome, I will give a contradiction by saying that this algorithm is not stuck. I mean, so by definition, E final is the error on which the algorithm stops. Okay, so if I find a valid flip for this algorithm, then this is a contradiction. Okay, and so the way to do that is to say first, imagine that we had a syndrome which is 0. Okay, then because E final, I can assume it's small enough because I started with something small enough. Then I just assume I run it, and I consider the set of the run of this algorithm, and I consider the set of f's that are flipped. Okay. So notice that if I look at the first element that was flipped, this is not necessarily a valid flip in our setting because there is errors on the syndrome. So what I'm observing might not coincide with the real syndrome of the error. Okay, so this might not be a valid flip, but still what you can show is that one of these flips will be a valid flip. Okay, so yeah, maybe let me not get into this. Basically, using expansion properties, you can use that one of these flips will be a valid flip even if there is a syndrome error. Okay, so now let me get to the analysis of the small set flip decoder when I have random errors. Okay, so what we've done so far is that the small set flip can handle errors of size root n on the qubits and on the syndrome. But of course, what I want is, what I will typically have is a linear number of errors because my noise rate is constant. Okay, and as I said, so it turns out that the minimum distance is really root n. So I really have to use the fact that the errors are random, not like the classical case where it even worked for arbitrary errors. Okay, so for that I have to define a model of random errors on the qubits and the syndrome. It turns out that the convenient model is the local stochastic model that was also introduced by Robert on Monday. Is the following: is that the probability that a given fixed set is a qubit error and t is a syndrome error goes down exponentially in the size of S and t. Okay, so let me at least formalize what the main theorem is that we show here about the small set flip is the following. So I'm using the same notation. E final is the error you obtain after applying the small set flip. It's that if you start with a pair which is local stochastic, okay, with some parameters which are bounded by some thresholds, then with high probability, the final error is also local stochastic. I cannot guarantee that the final error is 0, but I can control it in the following way, that I can guarantee that it's local stochastic with a parameter which is controlled. So for example, I can fix it to be P0 over 2, where P0 is this threshold starting from which it works. Okay, so again, very high level overview of how to handle random errors. I mean, the very high level idea is that if I have some errors which are far apart in the factor graph, then if I apply the small set flip, they will not interfere. The correction of the two will not interfere. So in the sense that if I was able to correct this error on its own and this error on its own, then I will be able to correct the two errors when they come together. Okay. Okay, so yeah, very schematically, let's assume these are the possible bits and qubits of my code. Okay, let's assume I have some errors in these red positions. Okay, so we know from percolation that because the graph has constant degree, that if I look at the largest connected component of the error, it's of size at most log n. Okay, so so this is good, but this is not quite sufficient for what we need. What we need is something a bit stronger, is that not only all connected components have size log n, but all connected components having a large overlap with the error have a small size. Okay, but this, it turns out, you can also show with similar percolation techniques. Okay, and so using this thing, you can show that what you will have is basically you will have this big error of linear size, but it's composed of these small connected components of size log n. Each one of them, you know how to correct it because it's smaller than root n, and so you will be able to correct the big error. Okay, so yeah. Okay, so let me conclude. Okay, so I try to show you that you can achieve constant overhead in memory fault-tolerant quantum computation using these expander codes, and the important properties were constant rate, LDPC, and efficient decoding. In particular, in this work, what we are focusing on is the efficient decoding. And yeah, so there are other features of this decoder that I didn't talk about, or at least I didn't mention explicitly. So one thing that I mentioned is that you use the exact same decoding algorithm even if there is syndrome errors. Okay, so this is sometimes called single shot property of this code together with this decoder. Okay, one thing you can do is that you can, this decoder actually can be parallelized to run in log n time. Okay, this is particularly important because remember, this decoder, you're applying it at every step. So after each logical gate that you apply decoding. Okay, so you want this to be fast. And even if you don't want to assume that the classical gates are faster than the quantum gates, you can even not do the decoding completely. So the decoding completely would need log n time. But what you could do is you could do only a constant number of steps. Okay, this will not completely correct the error, but it will decrease the error sufficiently that you can continue. Okay, so okay, so I didn't talk about parameters at all, explicit parameters. Yeah, they're very bad. But yeah, I invite you to see the talk of Lucien later today for numerical estimation of these thresholds. And just some interesting questions, I think, is that, yeah, so this construction uses polylog n blocks. And yeah, I don't know, is there a code where you would use just a single block? I think this is interesting. I didn't talk at all about overhead in time. So is it possible to get at the same time overhead in time and in space? This is an open question. Okay, thank you.
Okay, let's take a couple of questions.
So if the small set flip algorithm works, does it imply that belief propagation with the same errors and everything would work? Or is there some pieces that would not fail with the belief propagation?
Yeah, no, it doesn't mean that belief propagation would work. And I think there are settings where it doesn't work. I mean, exactly, Lucien will give a talk about this, and where he shows that if you use belief propagation on its own, it doesn't work well. But if you combine belief propagation with small set flip, it does work well. So no, they're not the same, but they're complementary, it seems. So.
Thank you for a very nice talk. I have a question. So in poly channel, you actually have correlation between X and Z part, and as I can see, you separately decode X and Z part. Have you tried to construct a decoding algorithm that works?
Yeah, no, yeah, that's a very interesting question, but yeah, we haven't tried to do that yet. Thanks.
Thank you.
Okay, let's thank Omar. Well, okay, one more question.
So classical LDPC codes, if you do something like this, can at least provide a fault-tolerant memory against even adversarial errors. Like if you let the adversary mess up n over 100 bits in every round. Certainly this won't work quantumly. This construction won't protect against adversarial errors quantumly. Do you think it could be improved to do that, or do you think that should be impossible?
Well, this is related to this big open question that was mentioned. I mean, you mean for a fault-tolerant setting, or fault-tolerant? Yeah. So
yeah, let's say fault-tolerant.
I think we only know how to handle LDPC codes. So this would mean we need to construct LDPC codes with constant linear linear minimum distance, and this is a big open question.
Right. So it's even harder. So maybe proving impossibility is easier than showing it.
You mean okay? So you mean, is there an impossibility in this direction? Okay, yeah, it doesn't seem much easier than showing that LDPC codes don't exist of linear minimum distance. So it seems that it's basically the same question to me. But
okay, let's thank Omar.